Welcome again to magnetostatic fields. Today we are discussing about Ampere's law and third Maxwell equation. So let's have a fast recap about our learning map. So far we have discussed many things about Biot-Savart law and discussed many of its applications. We have dealt with our inputs such as current or surface current, and we have dealt with quantities such as magnetic field and magnetic flux density. This time we will go with another law in electromagnetism or electrostatic, which is Ampere's law, and we will deal also with Stokes theorem to derive the second Maxwell equation. Ampere's law, or also known as Ampere's circuital law, states that the line integral of the magnetic field about any closed path is exactly equal to the direct current enclosed by the path. So if we have some cable and we have whatever current here, I, we name it I enclosed as written here. So if you would take any closed path such as circle, square, or whatever random path, but at the end this path is closed and surrounded this cable, you will find that the integration over this path, closed path, of hd dot dl equal to this I enclosed. So we'll have a fast recap about Stokes theorem and then derive the Maxwell equation related to Ampere's law. And after that, we will take one example about Ampere's law. So Stokes theorem fast, we have studied this several times. So if you have a vector f and you are integrating over a closed contour over dl, this you can rewrite this as derivative of curl of f dot n ds, and s is just the surface enclosed by the contour. So this was the contour, and the surface which is enclosed inside here is our surface. So to derive the third Maxwell equation, we will start with the Ampere's law, which states that the integral over a closed surface h dot dl equal to the enclosed current inside. And we recall that I enclosed is nothing but double integral j dot n ds. So you can take the left hand side here and equate to the right hand side here. Then at the end you get integral over a closed path h dot dl equal to double integral of j dot n ds, which is the third Maxwell equation. Now we move to the other form, which is a differential form, or what's called point form. And this is possible by applying the Stokes theorem, which we just recapped in the previous slide. So you start with integration over the closed surface h dot dl. If you take curl of h, then you can convert the single integral here to a double integral, and it become a surface integral. Then you take the left hand side here, equate with the left hand side here. Then you will get similar integral, I mean double integral over the same surface. Then you can conclude that what is inside here is equal to what is inside here. Then at the end we conclude that curl H is equal to Js. And again, this is either named point form or differential form of Maxwell equation. So we will conclude with one example on Ampere's law, which is basically the infinite line of current, which we studied before discussing Biot-Savart law. So we have this one extended from minus infinity to infinity, and it carries a current I naught in the direction of k. And due to the symmetry and the finite extensions, we'll find that this magnetic field is neither dependent on phi or z. This come from the infinite extension, and this come from the symmetry here. Likewise, we know that the field will not be in the direction of k because current itself is in the direction of k. So it can be either in rho or phi direction. But since the vector perpendicular to the line is in the rho direction, you will find that the field itself will be in the phi direction. So we can conclude that we only have one component which is in the direction of phi and is dependent only on rho. What's left for us to apply? Let's write Ampere's law here. H dot dl equal to I enclosed. So we need to know how H appears, and we need to know what is dl. So dl itself comes from the curve here, this curve which we are observing the magnetic field at. And we assumed it is a circle, so we need to calculate dl for the circle and more precise for the component when where we move. So we are moving in a circle here with a fixed rho. So we what is changing here is phi, more precisely. When phi changes, we need to look the to the arc length here. So this is our arc length. So this is just a fast revision about this, how to calculate the dl for phi. So normally your phi equal to the arc length L divided by rho. So you can rewrite this one as L equal to rho d phi, rho multiplied by phi. And now when you take the derivative, dl, rho is independent here, so you get d phi. So that's from where you got rho d phi. And finally, it is in the, since we are moving in the phi direction, you will get phi here. So we will substitute with this quantity and this quantity in the Ampere's law, like what we can see here. And phi multiplied dot product with phi, it will result in 1. Whatever inside here is just this quantity, and rho you are integrating over phi, so this appear as constants here. So at the end you will have only integration from 0 to 2 by d phi. If you do so, you will find this one is equal to phi from 0 to 2 pi. Substitute 2 pi minus 0, and you will get 2 pi. As you can see here, current is just I naught, so you substitute with it. What we seek is this calculation of this quantity. So if you divide by 2 by rho, you will get that as a function of rho equal to I naught over 2 by rho. And finally, we need the complete field, which is H equal to I naught over 2 by rho in the direction of phi. And this result is the same as what we have achieved when we have calculated the field using Biot-Savart law. Thank you.